class been? I am doing attendance as well, just so everyone knows. I'm sure you're all aware of that. Sweet. So, introduction to Earth science. What is that? Well, basically, I'm going to talk about every possible thing on this planet in a semester. It's going to be kind of brisk, but hopefully you're going to learn a little bit. My intention with this class is, again, not necessarily to make sure that you can understand if I give you 15 gray rocks, what those names, scientific names of those rocks are. That's not the point of this class. The point of this class is to give you a good understanding of the subject, hopefully a bit of an enjoyment of the subject. And if at the end of this class, besides your A, you go out for a walk and you take a few extra moments to look at that nice little outcrop and look at that cool little cloud formation above and think about what's going on, I'll be happy. So, Earth systems. There are 4 main spheres that we cover for the Earth here. So I can do some attendance for chance. I'll get over here, attendance thing. There we go. Sweet. There are 4 main spheres that we talk about when we discuss the Earth. The geosphere, hydrosphere, atmosphere, and biosphere. I probably don't need to explain what those mean, but I will. The geosphere are essentially the rocks of the Earth, the solid part of the Earth. You walk on the geosphere. We construct materials from the geosphere. It's the geology, right? Geogeology. The hydrosphere would be all the water associated with the Earth. If the geosphere is the solids, the hydrosphere are the liquids. That includes groundwater, ice caps. I guess if you really want to get into it, you could argue molecular water, things along those lines. The atmosphere would be the solid liquid, the gas part of the Earth. This is what we breathe. Take a big deep breath in, you suck it into some atmosphere, right? And the biosphere would be everything that's not in those first 3 spheres. Essentially the living organisms. We as living, squishy, membraney creatures have a little bit of geo, hydro, and apno in us. We're the last of the 4 realms of the Earth. I'm not going to cover biosphere very much. Most everyone around you, most all of you are going to probably take a bio class in some way, shape, or form. You'll cover it more then. Here is a also pretty cartoon explaining the 4 spheres of the Earth and the interrelationship between them. They all play together very nicely, right? You can't have an atmosphere without a geosphere. You can't have a biosphere without a hydrosphere, and etc., etc., etc. This class starts primarily by going through the lithosphere, by going through the geology of things. And that's, of course, the majority of the class as well. Eventually, we do cut into the hydrosphere and then end up at the atmosphere before going off into space, hopefully, for a little bit. That should be exciting. But this interworking relationship, all 3 of these playing a part with each other, it's how this world functions. And believe me, you're happy they all function together. Life would suck if we couldn't breathe, right? That would not be fun. Within this particular realm, we can see the size differential going on in these 4 spheres. The geosphere is arguably the largest of the spheres in a way that actually matters. The geosphere goes the entire radius of the Earth from the innermost core at the center, which we'll discuss about, the inner iron Earth radioactive core, all the way through the outer core, the upper mantle, the lower mantle, finally get up there to the crust. We live on the crust. The deepest we've ever dug is just into the crust. No one's actually physically seen with their eyes the mantle or the cores because they're just too deep and everything starts to boil off and melt. I'm sorry, your favorite stupid sci-fi movie, Journey to the Center of the Earth, The Core, what have you, that's not how it works. And The Core is a horrible movie. Do not suggest watching it. Within, on top of the crust, that is where we find the other spheres, specifically the hydrosphere. Most commonly, you're going to think of lakes and oceans with this. Lake Superior is part of the hydrosphere, right? Beyond that, rivers, groundwater, iceberg, ice sheets, whatever, we'll talk about that. If you go up above the geosphere and the hydrosphere, you enter the atmosphere. Again, the gaseous part. 99% of the atmosphere, particulate-wise, lies within 30 kilometers of the surface. The atmosphere itself has hydrosphere elements in it, right? Clouds, water, rain, snow, right? Pretty basic stuff. The atmosphere, technically, depending on how you want to define it, can extend past the moon. If you want to define atmosphere as molecules of gas that are held within Earth's gravitational orbit, the atmosphere extends thousands of miles past the moon. But that's not really useful. Sure, there's 2 molecules of oxygen way out that far. That doesn't matter much to me. So we tend to think of the atmosphere as the thick gas, right? The 30 kilometers or so above the surface that most everything works within. And of course, you have the biosphere sitting within all this, birds in the atmosphere, squids down the hydrosphere, earthworms through the geosphere, and us sitting here watching this Zoom presentation. And I guess you guys are probably all in your dorms by this point. So let's dive a bit deeper into these 4 spheres, starting out with the geosphere, the solid Earth. You may have learned about in high school science class the idea of the planets condensing around the gravity of an object at the beginning of the solar system, beginning of the galaxy, coalescing, if you will. That is the standard model for the formation of planets. You have Big Bang happen, expansion of space-time, what have you. We'll get a bit more into that later on in the chapter. But all these clumps would essentially be drawn towards each other due to gravity. If you know the equation of gravity, it refers to the masses of 2 objects and the distance between them, right? G m1, m2 over d squared. This gravity pulled together all the various clumps and plasmatezzles and all the other planetismals, I can't pronounce that word, whatever, all the other parts that were floating around to form what eventually would become our planets. That stuff that coalesced together and formed together, that dust, gas, what have you, created both the gaseous giants and the rocky subplanets, Mars, Venus, and of course, Earth. Within the Earth itself, we have, as I spoke about before in this picture here, where's my pointer? Huh. Ah, well. Within the planet itself, you guys can probably see my mouse here. Within the planet itself, we have these subdividers. That's what I was looking for. We have these subdividers. That's what we're talking about here. The Earth as itself, the geosphere, is comprised of a dense metallic core, as shown here in yellow, and that core itself has a inner and outer part. The inner core, the very, very center of the Earth, is a very, very dense, highly radioactive mixture of super, super ridiculously dumb hot iron and nickel. Beyond that super dense, super hot inner core, you have a liquid outer core, which is composed of some of the same metals. It varies as you get further and further away and in relative location. And that's what we're going to be calling this guy here, outer core. Very hot still, less hot the inner core, but liquidy. And then on top of that, we have a mantle. And the mantle is really weird because the mantle is what separates the outer core from the crust. And the mantle is solid by definition, but it's very malleable, very plastic-like, flow, if you will. It's a solid, sort of like if you could imagine rock, but has the motion of like a honey or molasses. That would be a not technically accurate, but not wrong way to describe the mantle. And since the rocky mantle has this movement capability to do it, albeit slow, and it's standing on top of here an outer core of liquid, that means any motion down here in the outer core can transfer through the mantle and to the crust. And this plastic slow motion brings you up to the crust, and this is, as we'll get into, is the plate tectonics, earthquakes, mountain building, orogenies, what have you. That's how this game is played. And of course, the crust itself, I'm sure we're all aware of that, right? That's what you walk on. It's what the ocean walks on. Well, sits on, rather. And it's by comparison to the other parts of the Earth here, it's very, very super thin. The go-to analogy for the crust of the Earth is that it's akin to the peel of an apple, whereas the flesh of the apple would be the mantle, and then the core of the apple would be the core. That's the size disparity we're talking about. So when I tell you that we've never dug deeper than the crust of the Earth, you can imagine how big the mantle is, given that we've gone so many miles deeper, we can't even reach the mantle. The mantle is such a big, vast, extreme amount of distance beyond that. Within the crust, we technically define it in two separate ways, oceanic or continental. I'm sure you can tell the difference without me explaining it. However, it is important to note that continental crust is thicker because, right, it's the continent, but it's also less dense, whereas oceanic crust tends to be thinner but have greater density. So down here, this black layer with some lines in it, this would be oceanic crust, dense but thin. And here's your continental crust, which is thicker but less heavy, less dense. So when we get to these question slides in this slideshow, I'm not going to have you stop and answer them. I'll go through them, but I'm going to go through them kind of slow. So I would suggest you look at these questions, make sure you can answer them. Heck, write them down if you want to. Make sure you know what's going on here before we move on. If you have any questions, of course, raise your hand, what have you. So what are the three major layers of the Earth? Well, we talked about that already, right? That would be the core, the mantle, and the crust. The outer core, inner core are different, but you can, in general, consider them a core. And then the mantle, again, has separations to it, but at this level of geology, you can consider it just the mantle. Which is / are composed of rock, which is / are metallic. Of those layers, the only one that's metallic is the core, the inner core. It is so incredibly hot and dense down there that metal that would usually be boiling is still solid. So it's, think your T-1000 from Terminator 2 sort of thing, right? And then the mantle and the crust would be rocky. Of those, the largest is the mantle and the thinnest is the crust. Specifically, the oceanic crust is the thinnest. Here are some very nice pictures of some of the varied geology we have. On the left here, we have the Grand Canyon. I'm sure we're all familiar. We've all seen pictures of the Grand Canyon. On the right here, the Baffin Islands and the Canadian Rockies. While these two pictures look very similar, their geologic history is vastly different. You notice the left one, it says sedimentary, and the right one, it says granite. Granite's an igneous rock. So even though they look very different, they're both very striking, their geology is an interesting example of the diversity that exists in the geologic world. Cool. So, continuing on this concept, let's talk the lithosphere. The lithosphere we define as the crust and the upper part of the mantle. So, we are talking the crust here and this section shown here. We're going to refer to that as the lithosphere. All right. The lithosphere averages about 100 kilometers thick and is broken up into 7 major and 8 minor tectonic plates. You maybe have heard of tectonic plates or plate motion in the past. The lithosphere is what we're talking about when we say that. As I said before, the mantle has a sort of honey molasses-like motion to it, where it's still essentially a solid rock, but energy and waves can travel through it. This motion is what the lithosphere more or less rides on top of. The ground you are standing on right now is technically moving. It may be moving stupidly slowly, parts of a millimeter a year. It may be moving relatively quickly, up to a few centimeters a year. However, it is in motion. And it not only is in motion, it's also in collision and in destruction with the other tectonic plates around it. And it's in that motion because, again, it's floating. If you can imagine, what's something? You're boiling some macaroni noodles, right? And as it boils, the noodles are moving around, hitting each other, what have you. That process is very analogous to what's going on with the Earth, where your macaroni noodles, what have you. I think macaroni floats, right? The macaroni noodles that you have would be plates on the Earth, the North Atlantic plate, the Canadian plate, Pacific plate, what have you. And then the boiling water underneath is the moving mantle that's causing those noodles to float around and change their positions. You usually don't use macaroni with this analogy, but I think it still works, right? Here is an example of what I'm trying to convey. This is a very weird concept. I'll grant you that. The idea that we're actively moving because something hundreds of kilometers thick below us, some solid rock, is somehow actually plasticky and honey-like, that's being driven by a metallic radioactive core we've never seen. But our best science indicates this is actually what happens. I can get into that outside of class if you want with the seismics and what have you. But yeah, this is what goes on. So again, if you can imagine your pot of boiling water, down here, the inner and outer core, that'd be your flame source. That'd be your stovetop, right? It's producing heat. That heat is traveling through this mantle, which in the pot of noodles analogy would be the water. As it gets hot enough, right, you can see this convection flowing, moving around, right? The crust up here is solid, but broken into pieces. This would be your macaroni noodles, if you will. So if you have this motion down here from this heat source, this motion circulating around, going any which way it so pleases, it's gonna flow and drag this continent pieces, this crust, oceanic and continental, around with it. What's going on here, we'll talk about that more in later chapters. But it is important to have the base understanding of geology and how it functions, in the sense that the geosphere works on this base level of a pot of boiling water with some macaroni on it. Cool. That's geology. Talk about the hydrosphere real quick. Hydrosphere, we touched that middle end of this book. That is water. If you see water, you got hydrosphere, right? Oceans, glaciers, groundwater, streams, lakes, clouds, rain, snow, sleet, ice, hail, what have you. Within the land water that we have, the vast majority of that water is in the oceans. The oceans are big, right? If you ever seen the ocean, it's big. It's really big. Oceans are huge. They take up the vast, vast, vast majority of water in its liquid form that we have on this planet. If you take the oceans out of the conversation, you're left with, 2.5% of water that's not sitting in the oceans. Of that, the vast majority of that water is stuck in the glaciers in the North Pole and the South Pole. It's stuck as ice, right? If you take that away, you're looking at 0.63%, 63 hundredths of a percent of the total water is groundwater. And groundwater, by the way, is the vast majority of the usable water that we have. When you turn on your faucet, pretty much no matter where you are, you're drinking groundwater. It is the water that is, stuck in the ground, right? Name is sufficient. 1/100th of all the water, not fresh water, 1/100th of all the total liquid water we have on this planet is comprised of our streams, rivers, and lakes. Lake Superior looks big. I get it. Mississippi River looks big. I get it. That's 1/100th of the total amount of water. It's technically insignificant, but that little amount of water is still very usable to the entire biosphere, right? And then break that down to 1,000th of a % of the water is the atmosphere. That's your rain, your clouds, stuff like that. Very far spread apart. We'll get into that as we go. And then, of course, we talked a bit about this, but you have the atmosphere, the biosphere. Atmosphere is the gas you breathe. You're happy it's there. Mostly the Earth's atmosphere is a mixture of nitrogen and oxygen, but you do have some other gases involved, such as argon, carbon dioxide, what have you. When you breathe in or take a big, deep breath, you're breathing in not just oxygen. Oxygen is the thing that your body cares about, this thing that your body grabs, but it's not all that you breathe in. And in fact, when you breathe in a bunch of oxygen, not all the oxygen you breathe in is actually used by your body. A lot of that oxygen just falls right back out again. Pretty cool stuff. But this isn't a biology class. I'm not going to go into how lungs work, right? 99% of the atmosphere is concentrated within the first 30 kilometers above the surface of the Earth. Then it starts to thin very rapidly. This is due to gravity, right? The atmosphere is made up of molecules. Molecules have weight, so they are affected by gravity. They have a mass to them. The vast majority of these molecules don't have enough forward acceleration to get very far, so they kind of hang out, floating around, falling, and raising up again in the atmosphere. Beyond that, the further out you go, again, you do find pieces of our atmosphere. If you want to define atmosphere as molecules of gas held by Earth's gravity, you technically go past the moon before you run out of those. But we don't need to worry about that too much. The atmosphere, right, that gives you your greenhouse effect, heats up the Earth. Birds live there, I guess, right? The biosphere is the last part we talk about. I don't go into great detail here, but the biosphere is all the living, breathing things, or most everything breathes, yeah. Biosphere, all four of these zones, all four of these spheres affect each other in various ways. All four of these spheres are interdependent with each other. You can't really have a geosphere without the hydrosphere and biosphere affecting it to create the wonderful landscapes that we see. Can't have a biosphere without an atmosphere, etc., etc., etc. So these systems, these spheres within them, sorry about hitting my mic there, these spheres in them have systems. We're going to define a system as an assemblage or combination of interacting components that form a complex whole, right? Good example of this would be the human body. The human body has a bunch of different systems in it, right? The skeletal system, the endocrine system. I don't know. I'm no anatomist, but hopefully you understand where I'm going with this, right? You can divide a sphere into a system, and likewise, this is a way we can use to provide context to what we talk about. Spheres are subdivided into component systems. For example, the surface systems are mainly solar powered. Where do you think plants get the energy to grow? From the sun, right? Mass energy move around, and this would be a system within the spheres that we're talking about, the water cycle, things along those lines. Terminology, more or less, right? The size of the systems that we talk about varies very drastically. So when I talk about a system, I could be talking again about the system that a plant uses to grow. It's very small, isolated. The light comes from the sun through the atmosphere, hits the plant that's in the biosphere while it's rooted in the geosphere. The nutrients from the soil are brought in, and the hydrosphere waters it, right? That's a very small, localized, tree system and all the interactions with that. We can also talk about systems like mountain building system, where the Himalayas come from, right? Half a continent spanning system of destruction and collision going on there. But those systems all, again, interact and work with each other. Very fun and exciting ways. And again, this is the introductory chapter, right? We'll go more into this as we go. So if I was to define a system, what would I do? Well, a system is an interconnected group, as a group of interactive and connected devices, situations, things that work and play with each other. That's a system. There's many different systems within a sphere, and they all interconnect and work with each other. Pretty straightforward, pretty simple. Explain the statement: matter can be recycled, but energy cannot. That's an interesting one. Wow, that's it goes a bit beyond what I've covered so far. But essentially, this goes a bit into physics in the sense that what we have on Earth, the material that we have on Earth, has always been on Earth, right? The rocks that exist on Earth have always sat on Earth. The biosphere that we have, the hydrosphere we have, is more or less always sat on Earth. But alluding back to that plant, that tree analogy earlier, that the tree system, the tree uses many different systems. It uses the geosphere to collect its nutrients from the soil. It uses its hydrosphere to collect liquid water to help it grow. Right? Those are systems that stay on the earth. Right? They recycle. The soil is the nutrients in the soil came from previous things that had died there. Right? However, the sunlight that came from the sun. The sunlight is used by the plant and then goes no place else. The sunlight does not leave the plant and go on further and further along. The plant uses that energy. It's, glucoses and sucroses, what have you. It's chemical processes, chemical systems. There we go. In a very unique and informative way. Hopefully this kind of gives you an understanding of what I'm talking about here. It's kind of hard to cover introductory concepts this vast, this wide, because remember, I'm trying to discuss the entirety of the Earth in one semester. That's a lot, right? But yeah, that's the process of spheres and systems. A good way to understand these processes and how big and vast they are is, of course, to talk about scale. When I talk about, say, geology, I use a metric for time that is so vastly different from anything else you've ever had to deal with. It is crazy. Only topped really by astronomy. And to understand what I mean by time on a geologic scale, we should probably go back to where this thought first originated. James Hutton is widely considered to be the father of geology. One of the first people to look at the rocks of the earth and say, I wonder why, I wonder who, I wonder how. Before that, rocks were, well, that's just the way God made it. No more questions to be asked, right? James Hutton thought a bit deep about this. Specifically, he noted erosion as a function of time, meaning the longer a river flowed, the deeper the river channel got. Maybe there's a connection between the river flowing and the channel getting deeper. So if I go and I look at something, let's say, as big as the Grand Canyon, and I see a river flowing through the center of that, maybe we have a connection. Maybe since this Grand Canyon looks like a super big version of the river in my backyard, but rivers do one thing, they cut river valleys. Maybe this was done by river over a very long amount of time, just as the river in my backyard is working. There we go. We now have a concept of geologic time. So we know how geologic time first came about as an idea. We can talk what geologic time is in relation to the spheres we talked about. The Earth is generally considered to be about 4.6 billion years old. That is a stupid amount of time. That is a crazy, 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 dumb, stupid amount of time. That is a nuts, crazy, I can't believe it's that long, amazing amount of time. 4.6 billion years is impossible to fathom. Life has only existed about 3.8 billion years. We have 800 million years of Earth history. that nothing happened. The biosphere did not exist for 800 million years. That's pretty impressive, right? And 3.8 billion years ago, you have your first single cellular organisms, your algae, what have you. And then eventually we got to us fine folks here today learning via Zoom. Skipped a few steps along the way, of course. This is a chart you're going to see a lot in geology classes. You probably also see in some biology classes if you go into the history of species. But what this chart does is it breaks down the entirety of known history into eras, periods, epochs. What these are ways to define big chunks of time without having to use numbers, essentially, right? Classically, we use this in a geologic scale. We have here Precambrian and here Phanerozoic. These are eons, massive amount of times. The differentiation between Precambrian and Phanerozoic is the type of life you have, right? Your Phanerozoic is your multicellular organisms, your creatures. Your Precambrian is mostly derived by, here, we can look down here, Protozoic, right? Protozoa is a type of single cellular organism. What existed during the Protozoic? Well, probably Protozoa, single cellular organisms. And then we're up here, Paleozoic, paleo, that sounds a lot like dinosaur fossils and creatures and stuff like that. That's because those two relate together. So the Phanerozoic is the geologic time scale that involves essentially something that looks like what we would see nowadays. Plants, creatures, what have you. That being said, within the Phanerozoic, for example, the Cambrian, that was the Cambrian life explosion. You have a huge chunk of the fossil record appears right here as the Cambrian. Within these individual sections here, up this nice little rainbow going up to the top, you have essentially separations of fossils, fossil types. We don't really get too much into the fossil record in this class, but it's still a super interesting topic. If you ever get a chance to read up or watch some quality documentaries on dinosaurs, heck, go watch Jurassic Park, the original. Don't watch any of the other ones. Go watch Jurassic Park. It is super cool stuff. Although the dinosaurs aren't exactly all from the same period, but whatever, right? Yeah, this essentially tells you a way to chop up the stupidly long history of the Earth. In case anyone ever asks you, we're currently in the Holocene, right here, essentially the time of humans. And the Holocene is within the Quaternary, which is within the Cenozoic, which is in the Phanerozoic. So there you go, the bar trivia for you. This concept of time is not necessarily a James Hutton invention. James Hutton realized that geology can be a way to describe things, essentially. But at his time, the world was running off of what we nowadays call catastrophism. Catastrophism is essentially the Noah's flood approach to Earth history. Something happened. Well, there must have been some big, massive, fast change to cause that, right? We go back here to the Grand Canyon. Well, water probably causes the cut, but that's pretty deep. So it's probably a whole lot of water doing this. Well, why would you say that? Why does it have to be a lot of water? Why can't it be a gradual little bit of water, right? Well, do we want to, what Hutton would do is Hutton would say, let's take some time, study this, look at this, and try to figure out which definition, which description of what happened best explains what I'm looking at. Do I find large floods of water causing things that look like the Grand Canyon? Or do I find small, gradual streams of water and rivers of water cause things like the Grand Canyon? These two different approaches, uniformitarianism versus catastrophism, were two ways to define the formation of the world. And truth be told, both of them are accurate, right? An earthquake is pretty catastrophic and pretty sudden and causes a lot of causes a lot of things to change, affects a lot of systems, affects a lot of spheres. Gradualism also works in that same way. Both of these are equally useful and equally accurate. Here we have some examples of earthquakes and tsunamis that have been very impactful. They're not only impactful, right? We think of these catastrophes as affecting how they affect the human life, right? The Haiti earthquake, tsunami of 2010, the Tohoku in Japan, that's 2011. That was the one that hit the nuclear power reactor, right? But these things have a massive effect on the rest of the biosphere, the hydrosphere, and the geosphere, and everything is involved with these great catastrophes. Volcanic eruptions, another big one, right? When we get into the rock types, I think in chapter 3, there's an entire classification of rock called igneous rock. That is basically volcanoes, and it's everywhere. Up here in the Keweenaw, we have lots and lots of igneous rock. We call it basalt up here. It's the gray rock you find that doesn't really look like it has any grains to it. That is the result of volcanic activity. And it's everywhere. It's huge. Volcanoes can cause a lot of damage. Threshold effect, feedback mechanisms. So when you have a catastrophe, when you have something big that goes down, it affects the world around it, as I said. How much does it affect the world around it? Well, that depends on how big and how fast and how detrimental the impact was. You have this idea of a threshold effect, i.e., the damage is going to only be so local until it hits a point where it's going to be a lot more than that. There's a very famous, I think it was like in the 1400s or the 1500s, a volcano erupted, I want to say in North Africa. I could be wrong, though. A volcano erupted. And it was such a large eruption that it actually affected the area around it to such a severe event that we had the ash and the effects of this volcano covered the continent of Europe and essentially took away a summer from the entire continent of Europe. There's murals and there's books that's written about how everyone thought the world was over because they didn't know a volcano erupted in a distant land, but the ash hung in the atmosphere for so long that the sun couldn't get through, and you essentially had a summer of darkness. That's going past the threshold for a lot of the systems involved, right? That's a single volcano did that, and it's very impressive. Mount St. Helens in Washington, we saw some of the particulate matter of that all the way in Michigan. Like it was dark for quite a while because Mount St. Helens was such a massive eruption. And this feeds back into itself, this feedback mechanism. If you have a volcanic eruption that takes over and covers, blankets essentially the majority of Europe, the biosphere is affected because the plants and the animals can't get the nutrition they need. That causes them to interfere less, dig less, grow less, hold the soil less. You're going to have that hydrosphere rain down. It's going to affect the geosphere, causing landslides, changing the topography of the locations that you are at. All these things play together, work together in a very amazing effect. Here we have a picture of a huge mudslide. Look at those size of those houses. Those are 2-3 story houses. Look how big that mudslide is. Absolutely massive, right? The hydrosphere rained down, caused the loosage of this rock. We'll go more into how mudslides work in later chapters, of course. In the, looks like chapter 10. Yep, weathering soil and erosion. But this landslide flowed down, definitely affected the biosphere around it, right? I see a lot of trees that don't exist anymore. Definitely affected those houses down there. Hopefully they weren't in them at the time. But this is an example of the geosphere, the hydrosphere, and the biosphere all coming together and clashing and doing something ridiculous. And naturally, of course, humans play a factor in this, right? We dig massive mines. We fish in the oceans, what have you. We definitely have a very dominant effect on the systems around us. And we tend mostly to think about how they refer to us, but truth be told, they affect everything. And that's something we need to consider, because if you get past this threshold effect for a particular system, such as the threshold of this hill, if you roll past that threshold, you could have major issues happen. In this case, you have a landslide. As shown here, the top one is climate change. We'll cover that near the end of the chapter, near the end of the class, chapters 20 and 21. But this is a very much a worry that you as students are having to deal with on a day-to-day basis. Here we have a graph of population for a large reindeer herd. What we notice here is it gradually grows and grows and grows until something happens and it collapses, right? What caused this event to happen? This is the kind of stuff that this happens to populations. You could think of reefs throughout the world that are bleached via either natural causes such as earthquakes or tsunamis, or man-made causes such as pollution that destroy entire reef populations, killing off the sharks, the plankton, the fish, the jellyfish, what have you. So it can be pretty ridiculous stuff. This graph here shows the human population scale, and the point being, these two look pretty similar, right? That population spiked pretty high, and then something happened and made it fall. Our population has been spiking amazingly ever since the advent of essentially the industrial age and modern technology, right? We have jumped, and I think now population's over 7 billion. We have jumped some 6 billion people in the past 200 so years. The past 4,000 years before that, it took us to reach 1 billion. Something to consider, something to keep in mind. Current trends to consider given humanity. Again, I'm not going to go into the geography aspects of this and the human cost aspects of this. That's better saved for other classes. I want to talk more about the mechanisms involved from a physical standpoint relating to those 4 spheres and the interconnected systems within them. However, that being said, it is worth noting that graphs can raise, graphs can fall. This technically is gradual. That drop off there, that's a catastrophe. And we know both of these interactions play with each other in what we deal with. Again, we'll cover the ideas of how to resolve some of these issues from an Earth history standpoint going forward. Maps here to show you if you care to read that. Cool story. This is important stuff. I don't want to take away from the importance of this concept. However, I do want to say that these are very big topics. So I'm going to end the recording now and go into a couple other things before the class ends. Does anyone have any questions for me before I halt recording? No? All right. So I will stop recording.